The question of whether NMN, nicotinamide mononucleotide, is merely an overpriced derivative of niacin, or more generously, a redundant alternative, demands a careful look at their respective metabolic routes into NAD, nicotinamide adenine dinucleotide. While NMN is often portrayed as a cutting-edge NAD booster, it is biochemically downstream of NR, nicotinamide riboside, and NEM, nicotinamide, both of which in turn ultimately converge on the same cellular endpoint, NAD. When juxtaposed with niacin, nicotinic acid, which enters the price handler pathway to make NAD through a more direct and energetically efficient route, NMN begins to look more like a sophisticated, but potentially superfluous, middleman. Its metabolic complexity, coupled with a high price tag, raises fair questions about whether it offers unique therapeutic value or simply capitalizes on marketing appeal. To unpack this, let's start with the pathways themselves. NMN is synthesized in cells from NR by the enzyme nicotinamide riboside kinase, NRK, and is then converted into NAD by NMNAT, nicotinamide mononucleotide adenylyl transferase. However, when NMN is taken as a supplement, it may not be directly transported into most cells. Evidence increasingly suggests that extracellular NMN is dephosphorylated into NR before entering cells, particularly in mammals, where high-affinity NMN transporters, such as SLC12A8, are not universally expressed. Once inside the cell as NR, the compound must be rephosphorylated to NMN and then proceed to NAD. This circuitous route undermines the narrative that NMN is more bioavailable than NR or other precursors. In practice, NMN supplementation may function primarily as an NR donor. Compare this to the route from niacin to NAD. Niacin is converted via the price handler pathway into nicotinic acid mononucleotide, NEMN, then to nicotinic acid adenine dinucleotide, NAD, and finally to NAD. These transformations are enzymatically straightforward and highly active in key tissues like liver, kidney, and immune cells. Importantly, this pathway avoids the need for NEMPT, nicotinamide phosphorybosal transferase, the rate-limiting enzyme in the salvage pathway through which NEM, NR, and NMN must pass. In states of stress, aging, or chronic inflammation, where NEMPT activity may be compromised, the price handler route offers a stable, NEMPT-independent method for sustaining NAD levels. This gives niacin a biochemical advantage in contexts of systemic metabolic dysfunction. Furthermore, niacin avoids generating a sudden excess of NEM during its conversion, reducing the risk of sirtuin inhibition. In contrast, the salvage pathway, NMN, NEM, inherently increases intracellular NEM, which needs to be either recycled or methylated for excretion, e.g., into NAM. This raises an additional metabolic burden on the methylation cycle and may introduce unintended consequences at high doses of NR or NMN. Thus, while NMN's proximity to NAD in the metabolic sequence may appear advantageous, it may also amplify downstream liabilities such as feedback inhibition and methyl donor depletion. On the issue of cost, NMN supplements typically sell for upwards of $40, $100 per month, while high-quality niacin is available for a fraction of that price. Yet in both cases, the outcome, raising NAD levels, can be achieved, and in tissues that favor the price handler pathway, niacin may actually do so more efficiently. Most studies comparing NR, NMN, and niacin in raising NAD show variable tissue-specific responses, but none demonstrate that NMN consistently outperforms niacin across the board. In fact, several studies indicate that niacin can raise NAD levels just as effectively, if not more so, in certain organs like the liver, spleen, and kidney. Moreover, niacin has proven clinical effects on cardiovascular health, inflammation, and neuroprotection, areas where NMN's efficacy remains mostly preclinical. The complexity of NMN's pharmacokinetics, including questions about oral stability, degradation into NR, reliance on specific transporters, and intracellular reconversion, complicates its value proposition. Add to this the lack of robust, long-term human outcome data for NMN supplementation, and the case for its high cost becomes harder to justify. Much of NMN's allure lies not in clear metabolic superiority, but in its position within a consumer narrative, advanced, novel, and marketed as a direct NAD precursor, even when that directness is biochemically questionable. In summary, NMN is not biologically useless. It does increase NAD levels in many tissues and may offer targeted benefits, particularly in scenarios where the salvage pathway is highly active. However, its convoluted route into cells, dependence on reconversion to NR, and metabolic redundancy raise legitimate concerns. When niacin can often achieve comparable or superior results through a simpler and more direct enzymatic route, and at a fraction of the cost, the conclusion becomes clear. NMN is less a revolutionary molecule and more an expensive derivative of niacin, repackaged for a market eager for innovation, even when the innovation offers no clear advantage.